Good morning, my dear students. In the last class, we have discussed regarding the what is the magnetic potential and the expression for the magnetic potential at any point on the axial line and equatorial line of a dipole. After understanding these 2 points, again we have discussed what is the meaning of permeability, susceptibility in detail. Is it we have discussed it in the last class. Now today, let us try to what is the discuss regarding the magnetic materials. Yes, already I made it clear that this magnetic materials topic, it is not a new one for you because already we have studied in what is the PUC level. I think both in physics as well as chemistry also. Now again, just to recall, is it this topic? Now, what do you mean by magnetic material? Any material which can be converted into the magnet. Such materials are known as magnetic materials. Depending upon their what is the behavior, isn't it? Depending upon the behavior of the magnetic properties, the materials are divided into three categories, isn't it? What are those? What are the three categories? Then those are, one is diamagnetic, second paramagnetic, is it third ferromagnetic. Depending upon the behavior of the magnetic properties, the materials, magnetic materials are what it is divided into three categories. What they are: diamagnetic, paramagnetic, and ferromagnetic materials. Now let us try to understand: is it to which we call it as a diamagnetic material? Is it a paramagnetic material and ferromagnetic material? After understanding this, all these, then we will discuss in detail regarding the properties of all these three what is the materials. One by one we discuss. Now, first let us come to the first material, that is diamagnetic material. Now, in this diamagnetic materials, they are the diamagnetic material whose initial dipole moment is zero. Such a material is known as the diamagnetic material. That is, the material whose initial dipole moment is zero, then such material is known as a diamagnetic material. Now, that means that in that material, initially it don't have any magnetic moment, isn't it? Now, it don't have any magnetic moment means how we can realize that there is what is the magnetic moment is zero, isn't it? Now, listen here. This we can realize that any material, isn't it? Whether there is a magnetic moment is present or not, how to decide it means we can decide it depending upon its magnetic behavior, isn't it? Now, you can see that iron is said, isn't it? Iron, it will be immediately attracted, isn't it, by the magnet. That means it has got the magnetic behavior. Similarly, steel also be to some extent it is what it is attracted. Nowadays, you are having the what it is the screwdrivers, isn't it? You might have seen it, isn't it? Then if you put a nail to it, then it attracts. Even though it is a steel rod, isn't it? When you what it is put it, isn't it, that screwdriver on the nail, it sticks to this one. Isn't it? That means the steel is also be having some magnetic property. Means this one. And similarly, there are some they are having some magnetic property, because of that reason only it gets attracted. Means what? It has got some magnetic property in it. That is, it has got some magnetic property means it has got some what it is the magnetic moment also be present in it, isn't it? Now, iron, it is more attracted by the magnet, means it is having the more magnetic moment in it. Then steel, as I have given an example of screwdriver made up of the steel. Then when you put a on the nail, it gets attracted. what it is the slightly means the steel is also having some magnetic property less. That means in that case there is a less magnetic moment is present in it. And there are some materials are there, then they not at all exhibit the magnetic property. Isn't it? Like what is a rubber is there, wood is there, like this. Is it any or this type of the other materials are also be there? Isn't it? They never exhibit, isn't it, any magnetic property. Then why me? Because in such cases, isn't it, the magnetic moment is zero. Isn't it? That means initial magnetic moment is zero. Are you following? Then see, to exhibit the behavior of magnetism, the very important quantity is magnetic moment must present in it. Isn't it? If there is a magnetic moment, then it exhibits a magnetic property, magnetic field, etc. Now, if it don't have any magnetic moment, then it will not exhibit any magnetic property. That means it will not produces any magnetic field. Isn't it? Then, which is having the more magnetic moment, then it has got the greater behavior of the magnetic property. Isn't it? Because you can see that the general formula of the magnetic field, isn't it? It is equal to what? It is equal to, on the axial line or equatorial line, you take it mu naught divided by 4 pi. Isn't it? For axial line, it is 2m divided by dq. Isn't it? Field along the axial line of a dipole. Then what is this m? M is a magnetic moment. Isn't it? Now, looking to this one, it is in the numerator. B is directly proportional to the magnetic. Correct? Isn't it? That means if it has got more magnetic moment, it produces some more magnetic field. If it has got less magnetic moment, it produces a less magnetic field. Suppose if what it is the M is equal to 0, if the magnetic moment is 0, then what is the what we get is B is also equal to 0. It will not produce any magnetic field. That means any magnetic behavior it will not exhibit, isn't it? Then why? Because magnetic moment is 0. Or if that is here, come to the point. Diamagnetic material is what? These are the materials in which the initial magnetic moment is 0. Initially, you don't have any magnetic moment. Then what will happen is when it is placed in a magnetic field, isn't it? When you place it in a magnetic field, then it gains some magnetic. It gains some magnetic moment. Then, yes, you know that magnetic moment is a vector. Already had told you, isn't it? Magnetic moment, it is a vector. The direction of magnetic moment is from north to south, etc. These are the points, isn't it? Already I made it clear, isn't it? Therefore, the when it is placed in the magnetic field, isn't it? It acquires some magnetic moment. Isn't it? In what direction means? In a direction opposite to the applied field. Isn't it? Then because of that, what reason that diamagnetic material gets repelled. Isn't it? Now if I show you in the figure. Now here, let us consider this is a what is the material. Then initially, isn't it? M is equal to 0 in this one. The initial magnetic moment is 0. When this material it is placed in the magnetic field. Now see, this is the magnetic field in this direction. Isn't it? Now, when this material it is placed into this magnetic field, isn't it? Then it gains some magnetic moment. Isn't it? Initially, you don't have any magnetic moment in it. Isn't it? Now, when it is placed into the magnetic field, then it acquires some magnetic moment. Isn't it? Acquires some magnetic moment in what direction? Isn't it? In the direction opposite to the applied field. Isn't it? That means if you apply the magnetic field in this direction, then the magnetic moment acquires in the opposite direction. As a result, isn't it? It gets repelled. It comes out. Isn't it? Therefore, this is the behavior of the diamagnetic material, isn't it? Next, coming to the second one, paramagnetic material. Paramagnetic, isn't it? Paramaterial, it is. This is paramagnetic material. Now, consider it as a paramagnetic material means then these materials have some initial magnetic moment. Isn't it? Initially, they are having the some magnetic moment. Isn't it? Now, that means when you consider here, then you can see that this is a material. Already it has got some magnetic moment in it. Isn't it? Already, before placing it into the magnetic field, already it has got some magnetic moment. Now, when you place it into the magnetic field, isn't it? This one, then isn't it? This magnetic moment, isn't it? Now it is having the random direction it is. Before placing into the magnetic field, it has got some what? No doubt magnetic moment it is same, but it has in the random direction. There is a random direction. Then when such a material it is placed into the magnetic field, then this magnetic moment aligns in the direction of the applied field. Isn't it? In what direction it aligns? It aligns in the direction of the applied field. Hence, isn't it? Paramagnetic material gets attracted. Isn't it? Then this is repelled. And this is attracted. This is the a paramagnetic. And the next is coming to the third one. Ferromagnetic, isn't it? Now here, in this ferromagnetic material, already it has the maximum or initial magnetic moment, isn't it? Already it has maximum initial magnetic moment. Yes, like that. But whatever the maximum initial magnetic moment is said, that is in the random direction. It is not aligned in a particular direction, isn't it? When such a material, it is placed in a magnetic field, isn't it? Into this magnetic field, then that magnetic moment aligns in the direction of the applied field, isn't it? In this case also, isn't it? Then this magnetic moment aligns in the direction of the applied field, and this ferromagnetic material is strongly attracted. It is weakly attracted here in case of the paramagnetic material, isn't it? And here it is strongly attracted, isn't it? Therefore, this is what the behavior, magnetic behavior of the diamagnetic, paramagnetic. Once again, I repeat here. In case of the diamagnetic material, the initial magnetic moment is zero. When the material is placed in a magnetic field, it acquires some magnetic moment in a direction opposite to the applied field. Hence, this diamagnetic material gets repelled. Next, paramagnetic material. This paramagnetic material, initially it is having some magnetic moment, When material is placed in the magnetic field, then that magnetic moment aligns in the direction of the applied field. Hence, it is what it is weakly attracted. Next, ferromagnetic material. This material has maximum initial magnetic moment. When the material is placed in a applied field, then that magnetic moment aligns in the direction of the applied field. Hence, the ferromagnetic material is strongly attracted. Isn't it? Therefore, this is what diamagnetic, paramagnetic, and ferromagnetic material. Now, let us try to understand about the properties of this diamagnetic, paramagnetic, and ferromagnetic materials. Isn't it? One by one, let us try to understand here. Now, first let us come to the properties of the diamagnetic materials. Property of diamagnetic material. Let us discuss one by one. Now, one more point is the tape. I want your attention here. When you understand the properties of diamagnetic material, then very easily you can write the properties of paramagnetic and ferromagnetic. Very easily you can what is the right, isn't it? Just first you try to understand, isn't it, carefully regarding the properties of the diamagnetic materials, isn't it? Now the first property is, isn't it? Yes, you know that in this diamagnetic materials, initial magnetic moment is zero. Isn't it? This is not zero. Initial magnetic moment is zero. When such a material it is placed in the applied magnetic field, it gains some magnetic moment in a direction opposite to the applied field. Hence, it gets repelled. Isn't it? That is here initial magnetic moment is zero. Initial magnetic moment is what is zero. When such a material is placed in the applied field, it gains a certain magnetic moment in a direction opposite to that of the applied field. Hence, diamagnetic material gets repelled. Isn't it? This is the first constant. And the second property is when this diamagnetic material is placed in a non-uniform magnetic field. Isn't it? When it is placed in a non-uniform magnetic field, it moves from, isn't it, the strong to weak region. Isn't it? That is here when it is placed. It means what? Diamagnetic material. When it is placed in a non-uniform magnetic field, non-uniform magnetic field, it moves, isn't it? It moves from where to where? Strong to weak region. Weak region. Now listen here, non-uniform is what? Magnetic field is not uniform. It is not same. Means what? Somewhere it is more, somewhere it is less. Like that. Okay. That means in some region the magnetic field is strong. In some region the magnetic field is weak. Isn't it? Now, if you consider here like this one, then in this what is the region the field is strong, isn't it? Then I have represented this as a thick, and whereas this is what it is a weak. Isn't it? Now, when you place it is the diamagnetic material here, then it moves. This is a strong and this is a weak. It moves from strong to weak. This is the second. And the next, the third is here susceptibility of these materials. Isn't it? Susceptibility of these materials is what the or otherwise in a what is short form I will what it is mentioning you that these materials have negative susceptibility. Isn't it? Negative susceptibility means susceptibility it is represented by what is the chi is what is the negative. Isn't it? Next, B is susceptibility is independent of the temperature. Isn't it? This chi is what it is the independent of temperature T. That means susceptibility it does not depend upon the temperature. That means whether you increase the temperature or decrease the temperature, susceptibility will never changes. Isn't it? This is what the meaning. Next, E. The next property is that these materials or permeability of these materials is slightly less than 1. Isn't it? That is mu. Isn't it? Permeability of these materials is what it is slightly less than 1. Less than 1. Isn't it? This one. And this is the one. And the next is when a watch glass, that is in chemistry laboratory, you might have what the use of the watch glass. That means there is a glass plate type, isn't it, in which you use the any what is a compound, isn't it? That is what we call it as a watch glass. When liquid diamagnetic material, or when a watch glass containing the liquid diamagnetic material is placed between the two magnetic poles, like this one, then the liquid depresses at the center, like this. The liquid depresses at the center where the field is strong. Magnetic field usually is strong in the midpoint, isn't it? Therefore, strong magnetic field is there. Therefore, level of the liquid, what it is, there is a depression index. Usually, when you take the water glass, then this is the level of the liquid will be unit. But when it is placed between the two poles of a strong magnet, the level of the liquid decreases at the center where the field is strong. And the next property is the here when a U2 containing liquid diamagnetic material is placed between the two powerful magnets. This is the and this is the stop. When or we call it one limb of, that is this one, is one limb of U2 containing liquid diamagnetic material placed between the two powerful magnetic poles, the level of the liquid decreases. Isn't it? Level of the liquid decreases. Isn't it? In what way? When you take out it, then levels in both sides will be same. When you take out from the magnetic field. Isn't it? Now, when you place it like this one, then you can see that the level of the liquid decreases here. Now see, these are the properties of what is the diamagnetic materials. Once again, repeat here. The first is what? Then in case of the diamagnetic materials, initial magnetic moment is zero. Initial magnetic moment is zero. When such a material is placed in a magnetic field, some what is the magnetic moment is produced in a direction opposite to that of the applied field. Hence, the diamagnetic material gets repelled. First, second is what? When what is the diamagnetic material is placed in a non-uniform magnetic field, then it moves from strong to weak region. Non-uniform is admitted here already. Somewhere the field is strong, somewhere it is the what it is weak. When you place it, then it moves from strong to weak region. Next, third is these materials have negative susceptibility. Isn't it? Susceptibility is negative. And fourth is the susceptibility of this material, means diamagnetic materials, is independent of temperature. That means it is not dependent upon the temperature. Next, the next property is permeability. Mu is what? Permeability of these materials is slightly what is a less than 1. Slightly less than 1. That means in fractions you get. Is it 0.8, 0.9? Like that. Less means not that much less, slightly less than 1. That is what the word it is used. That means you will get 0.95, 0.967 like this. Next, when a watch glass containing liquid diamagnetic material placed over two powerful magnetic poles, the level of the liquid decreases at the center where the field is what is strong. Next property is when a what is the one limb of U2 containing liquid diamagnetic material placed between two powerful magnetic poles, the level of the liquid decreases. Isn't it? These are the properties of the diamagnetic materials. Now, yeah, already I had what it is they made it clear that if you know the properties of the diamagnetic materials, then very easily you can remember the properties of the paramagnetic materials. How means? Then you can see that the properties of the paramagnetic materials almost opposite to that of the diamagnetic material. Because from the definition itself, isn't it? We have discussed that diamagnetic material gets repelled, paramagnetic material gets attracted. Isn't it? So that almost all properties are like this only, isn't it? The properties of the paramagnetic material are almost opposite to the properties of the diamagnetic material. Now, so that very easily you can understand, isn't it, about this one. Now, here coming to the what it is the properties of paramagnetic material. Properties properties of magnetic materials. One by one, let it. Now here, from this only you can understand, isn't it? Then what is the first property? Yes, you know that in case of the paramagnetic material, there is a some magnetic moment is in. Here it is zero, but in this case, it is having some magnetic moment. When it is placed in a magnetic field, it aligns. It aligns in what direction? In the direction of the magnetic field. Whereas in diamagnetic material, aligns opposite to that of the field. But whereas here, it aligns in a direction of the magnetic field. Hence, it is what is the weakly attracted. That is repelled diamagnetic material, but it is attracted. Next. Second property is what? This one. When the paramagnetic material is placed in a non-uniform magnetic field, it moves from it is moves from strong to weak, but here it is a weak to strong. This thing, weak to strong. This thing. It moves in this direction. This thing. That is the second property. And the third property is what it is the susceptibility of this diamagnetic materials is negative, but whereas here we will get positive. This thing. The third. Let's see right here. Then is what it is this susceptibility is what it is the positive susceptibility is there. Okay. Next thing. Then D. Here it is susceptibility is independent of temperature, but here it is the depends upon the temperature. Then you see, whenever we say that it is a depends upon the temperature means how it is depending, that we must mention it, isn't it? Then how it is depending is that is whether it is directly proportional or inversely proportional. This is the way what we can understand. Then in this case, the chi depends on temperature. Then how it is depending is this chi, it is inversely proportional to the temperature. Isn't it? The chi is inversely proportional to the temperature. Next, here E, you can see that the permeability is slightly less than 1, but it is here slightly greater than 1. Isn't it? Mu isn't it? Slightly greater than 1. Greater than 1. And next, coming to this one, isn't it? When watch glass containing liquid paramagnetic material is placed over two powerful magnetic poles, then the level of the liquid what is the rises. Isn't it? In this case, you will find like this one. Like this. Rises at the center where the field is strong. Isn't it? Next, last property, right? That U2 containing liquid paramagnetic material is it placed between the two powerful magnetic poles, the level of the liquid increases. In this case, you will get like this. Now, these are the properties of what it is a paramagnetic materials. Yes, I have to do that. The properties of the paramagnetic materials are almost opposite to the diamagnetic material, isn't it? That is, if you remember the properties of the diamagnetic materials, looking to that very easily, you can write the properties of the paramagnetic materials. Right. Now, coming to the what it is a ferromagnetic material, isn't it? Then here, the properties of what it is the ferromagnetic materials. Properties of ferromagnetic materials. Now listen here. The paramagnetic materials and ferromagnetic materials, these two are almost to one another same, isn't it? So that we say the properties of the ferromagnetic materials are same as the properties of the paramagnetic material, but to a greater extent. Every property is little bit strong, isn't it? Like that is here in case of the paramagnetic material, we observe it has some initial dipole. Initially, it is having the some magnetic moment, but here it is has the maximum greater, isn't it? Then it is weakly attracted, isn't it? Then whereas it is the strongly attracted, isn't it? Strongly attracted, which one ferromagnetic, isn't it? Like this, everything, all the properties, that is the properties of the ferromagnetic materials are same as the properties of the paramagnetic material, but to a greater extent, isn't it? This is what we say. And you observe that the permeability is slightly greater than 1, slightly, but it is a more greater than 1, very high, like that it is. So that generally we say that the properties of the ferromagnetic materials are same as the properties of paramagnetic material, but to a greater extent. Now see, this is about what it is the magnetic materials, isn't it? Next, their properties. After understanding this one, I think this is the very easiest point to remember also. The, depending upon the behavior of the magnetic properties, materials are divided into 3 categories: dia, para, ferro. Then what is dia? What is para? What is ferro? Their properties, I made it clear that if you remember the properties of the diamagnetic materials, then very easily you can write the properties of the paramagnetic material exactly opposite. Then as far as the properties of the ferromagnetic materials is what? The properties of the ferromagnetic materials same as the properties of paramagnetic materials, but to a greater extent. This is it. Now see, after understanding this one, now let us come to the next point, that is the Ampere circuit law. Ampere's circuit law. Now, let us try to understand first it's the what it is a statement, and then we go for its a derivation. Statement and the derivation of this, what it is the Ampere's circuit law. Now listen here, the statement try to understand. It states that the suppose this is a closed curve. This is a closed curve in which the current is what it is flowing in a closed curve. Then statement of this Ampere's circuit law is that the line integral of line integral of B dot dl. B is what? Magnetic field. dl is the small length of the current. Line integral of then B dot dl over a closed curve, or you can write it as closed loop also. Carrying current is equal to is equal to mu naught times current carried by the loop. Current carried by the loop. Carried by B. This is the statement of what is the Ampere's circuit law. Once again, carefully listen here. What it says: line integral of line integral of B dot dl. Symbolically, in integration you might have studied that this way we represent the line integral of what is the B dot dl. Over a closed, what is the loop? Closed loop it carries the current is equal to mu naught times multiplied mu naught times the current carried by the. This is the statement of the Ampere's circuit law. Now, this is what we have to prove it, isn't it? Then very easily, we can prove, this law. It is not so much difficult. Now, here, for the proof of this one, let us consider this is a closed loop. Yeah? It carries. Now, here, let us consider this is a small length of conductor of length here, isn't it? Now, from this point, draw a perpendicular on this, isn't it? That's equal to what is the radius. Yes. Here, yeah, you know that the field per unit length, it is equal to what? Field per unit length due to a straight conductor. Due to a straight conductor is what is the due to a straight conductor. Straight conductor is what it is the. Let us take this as, you know that B is equal to, formula is what? Mu naught divided by 4 pi into 2I divided by D, distance is. But this distance is nothing but it is equal to the radius. Now, wait. Isn't it? Therefore, that is the field per unit length. That is unit length of this, what is the conductor, and how much magnetic field produces at a certain distance. This is a. Now you are applying for this one. Isn't it? Then we have taken an element, isn't it, of length equal to how much it is a dl, isn't it? dl. Then how much magnetic field is present here at the center O, isn't it? That is here the field at O due to AB is, isn't it? Is B, it is due to AB, it is equal to how much you get means. Now listen here. For unit length, B is equal to this much. For unit length. For 2 units of length means what you have to do? Into 2 you have to do it. For 3 units of length, it is 3 into this much. And for 4 units, 4 into this much. And for length here means what? Here. Now B is what? B is the magnetic field due per unit length. Then due field due to AB of length, I will write here, of length dl is equal to B into dl. Once again, try to understand, this much is the magnetic field due to a unit length. B is the magnetic field due to a unit length. For 2 units of length means into 2B, 3 units of length means 3B, 4 units of length means 4B. For the length of dl means what? Into dl. This much is. Therefore, here, this much is the magnetic field, isn't it? This much is the magnetic field due to what is the current element of length. Next, the total field at O at this point due to the complete loop, isn't it? Due to complete here, this much, that is B is the magnetic particle field per unit length it is. Then magnetic field due to the length dl, it is equal to this one, B into dl. Therefore, what is the total field, isn't it, here due to the complete loop, isn't it? Complete loop is equal to, isn't it? Then is equal to, what you get here is then summation of this time. Due to this much is how much, due to this much is how much, due to this much, this. You go on here, isn't it? Summation. That is the integration. isn't it, is equal to integration of, isn't it? That is, we are this type of adding this one as a line integral. We say symbol. Isn't it? Then what is the b into what is the d? Isn't it? B. Now this is equal to what I can write here. This integration of line integral of b into dl, it is equal to, then here we write what is the formula of the b that we write here, isn't it? Now when you this you can write it here as 2 pi, isn't it? Now this is equal to mu naught divided by 2 pi I divided by this. Now instead of b I will write this much here, isn't it? Now this is equal to how much integral, line integral of this mu naught divided by 2 pi, then I divided by r into what is the, this is the dl in state. Now the constant factors, is it take outside. Oh, now I can write this as this is equal to it is equal to, is it this as the mu naught divided by 2 pi I divided by r into, isn't it? This is now right, isn't it? Line of, then b is nothing but here mu naught divided by 2 pi in mu naught divided by 2 pi I divided by r into dl. This instead of b, is it a, I have written, is it a, this much here. Now this is equal to, now what you do is constant factors you take out of the integral. Mu naught by 4 pi is a constant, this much, sorry, mu naught by 2 pi. Next thing, I is also be a constant. In a given loop, whatever the amount of current it is flowing in this particular loop, that is also be a constant. And the radius of the loop, it is also the same, line of into dl. This is what we did here. Now this is equal to mu naught divided by 2 pi, is it I divided by r. Now integration of what dl, is it? Now you see the figure, this plus this plus this plus this, you go on adding, this complete gives what it is the circumference of the circular loop. Therefore this complete value, it is equal to 2 pi r, is it? 2 pi r. Now we can see that this 2 pi and this 2 pi will get cancelled, then this radius r will get cancelled. You left with what is the mu naught into I. This is what it is, line integral of b dot dl, it is equal to mu naught. Isn't it? This is the, isn't it? Now here this we have proved that the line integral of b dot dl, isn't it? Line integral of b dot dl over a closed loop carrying current, it is equal to mu naught times the current carried by the loop. This is the its proof, isn't it? Now see, this is the Ampere's circuit law. Then here, this Ampere's circuit law, it is having its own importance. Then what is its importance of this one? Then you will study in your the higher classes. Then I hope, is it this you might have understood. Now in this, what it is that today's lecture, we have what it is discussed regarding what it is the magnetic materials, isn't it? Then what are the magnetic materials, properties of the magnetic materials, and the Ampere's circuit law. Now I will stop here. In the next class we will discuss the next point. Thank you very much.